So welcome to Applied Data Analysis. This course is now cross-listed. So if you're in either TTP 201 or ECI 254, you're in the right place. If you're not in either of those classes, you're in the wrong place. Okay, so I'm going to just quickly go through some course logistics, and then this is the last time you guys are going to see any slides for the course. All right, so course information. So first off, everything that I'm talking about here, all of this information is posted on Canvas, mostly in the syllabus. But if there are any course logistic questions that you guys might have, feel free to ask me. You guys can always contact me by messaging on Canvas, or you can email me directly. Our class is going to be Tuesdays, Thursdays, 2 to 4 here. If you're here, you already know that. I'm not going to go through our full schedule here, but this information and a little bit more detailed description of what's covered in the topics is all available on the syllabus. What I will say is our first week, so just today and on Thursday, we're going to be covering kind of a introduction to R. So a lot of folks usually come in with programming experience, either in Python or R, and that's totally fine. And in fact, you are welcome to not attend this week if you feel pretty comfortable with your programming. I won't be offended if you leave after the course logistics. But I would say, yeah, for those who aren't, this is going to be kind of a quick foundational introduction to programming in R. If you don't have experience, I also would not be worried. Plenty of students in the past years have taken this class coming in with no programming experience, and they have done perfectly fine in the course. It just takes a little bit longer. Just know, so that as far as sort of feasibility, coming in with no programming experience, that's many students have done perfectly well. Okay, any questions or concerns so far? All right, so yeah, this class is mainly going to cover regression analysis, but we'll also look at a couple of other data analysis techniques, and it'll get a little bit more complicated as we proceed through the course. It is going to be more applied, and so who's taken either a regression class in statistics or like an econometrics type class in econ? A couple people. Yeah, and so those classes tend to be a lot more theory heavy. Here we're going to really focus on application. Okay, office hours. So my office hours are going to be from 10 to 11 in Gaussy. We have our fearless TA over here, Grant, and his office hours. Is this still right, Mondays? Yep. Yeah. So that's going to be out in West Village at the EV Research Center, a little bit farther out, but yeah, I think you guys should have no problems getting out there. If these times don't work for you, we are still open to scheduling and finding times that work, and so just let us know if you want to meet. But you can't make these office hour times. And then, of course, grading. Okay, homeworks are going to be 50% of the grade here. So there's going to be 4 homeworks. You get about 2 weeks to do each homework, and then just a flat 5% deduction per day late. There are no exceptions or exemptions unless you have medical, some kind of medical issue. Those are the only ones we'll have exceptions for. Participation, I'm not going to be keeping track of participation, unless you're just not here the entire class. Really, this is just a way of kind of buffering your grade. It can, sometimes make the difference, and if you've been participating, that's going to be the thing that can boost you over. But generally speaking, I would just not really worry about this part of your grade. And then the last piece is your final project. We'll have 3 components to that. If you've taken my other grad course, it's similar with the final project. So we'll have a project proposal, which is going to be due May 8th. Project presentations are due the start of the last week of class when you guys actually present your projects. And then the project report is due basically at the very end of the quarter. There's more details about the requirements for the projects that's already on Canvas. You can look at exactly what each of these entails, and then we have rubrics for grading those that are available on Canvas already. And also these projects are not necessarily individual. They can be if you want, but you are welcome to be in groups of 2 to 3 people, no more than 3. I guess we have a slightly larger class, so that'll be a little bit interesting for getting through all of the presentations, but we will make it work. Any questions so far? No. Okay, last thing that I'll say. Yeah, I guess I'm more diligent about kind of the way I think about AI in undergrad. For you guys, you're here to like learn this stuff. You can use, I'm open to learning with AI. I would just say that just be cognizant of the way that you're using it and how that's actually going to affect the way that you're doing the homeworks, because that's really, I think, where you're going to be doing a lot of the learning. I have run it over the years to actually see if it can do my homeworks. And at first, not so well. More recently, maybe it's able to do it a little bit better. Some things I think it's still not great at, so just be aware that, you should be checking on any usage of AI and using it carefully. Okay? Any questions, concerns? All right, that's the course logistics, and we'll kind of just jump right into it. So as I mentioned, today we are going to be doing this sort of tutorial to dive into introducing how to use R. So for those, I would encourage you guys to follow along if you can. I think I neglected to make an announcement prior to the start of class. If you haven't used this before, this particular platform is called RStudio. So you guys can go ahead and download this if you don't have it. You'll also need to download R, the sort of base version, in order to get this to work. But I'll go ahead and kind of describe some of the components of this particular interface. One moment here. Yeah, so on the screen right now, you can see there's kind of 4 sort of main components. It's divided in this way. It's kind of handy. All of these sort of 4 windows are helpful for different things. So kind of the first one to talk about is this one down here in the bottom left. That is the console or the terminal. This is where essentially you're doing operations. This is kind of the skeleton on which everything else is built around, right? And so I can use this. You can think of this almost as like as a calculator, essentially. So I can put in some kind of operation, 1 + 1 down here, and then we get 2. Is this font size okay for everyone? Visible? All right, great. Okay. One of the things that you'll note is that if you are writing code down here, blah, 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 and I'm like executing stuff, none of that code is actually saved. You're just like executing specific commands. And so up here, right above the console, this is called source. This is kind of like a notepad where I can write things, and I can save things that are on that notepad. I can send them to be executed inside of the console. And so if I say something like 1 + 1 up here, you can press this button here that says run, which will run the line that my cursor is currently set at, which is just line 1. And so I click this, and that executes that same command. As a shortcut on a Mac, you can press Command Enter to do the same thing, or on a Windows-based computer, Control Enter will execute that line. Okay. The other two windows. So over here, we have what's known as the environment or history. As you store certain things in your code as it's executed, so they're like objects that we can store, you'll see that appear in this environment, and it'll explain characteristics of the objects that are stored. And we'll talk in more detail about that in a little bit. And then down here, this is kind of like a set of different helper tools that are useful. So right now, it's on this plots tab. So obviously, if I decide to plot a figure, it'll appear down there. You can also navigate through different files. And we'll talk about why this is important, especially as I start to interact with files. I'll talk about help a little bit later on. But yes, these are just a set of general tools that are helpful for especially visualization of certain things. Okay, actually I should pull the class. So who's familiar with R? Okay, most people, and then Python, a couple people, great. And then for whom is this like completely new to? Okay, well, all right. So you let me know if I need to slow down, okay? All right, so basic commands and objects. Okay, so most of you guys, this should be simple. But hopefully we'll still learn a little bit even here. So give me 1 second. All right, so basic operations. So I can do addition, I can do multiplication. So if I want to do like 2 × 3, that's the asterisk. 3 to the power 4 using the caret. So these are pretty simple, kind of the simplest operations that you can do, very akin to, like I was saying, to like a calculator. We can also store data as objects. Okay, so for those of you who are primarily versed in Python, this might look a little bit different to you, but we have an assignment operator that uses a caret dash. So it's essentially an arrow that assigns objects. So here I've stored in an object I've defined as x as 2. And so if I go down to my console and I type x and I hit enter, it'll return the number 2. Okay? So I've essentially stored that object. And we can see over here in the environment values, we have x now stored as one of the objects, and then it's defined as this kind of one number. Okay. What about if I do capital X? What happens? Any idea? The whole class raised their hand for knowing R, so someone must know what happens. Yes?
Guessing this is not defined, so nothing will happen.
Yeah, object X not found. Yeah, and so if you put in an object that hasn't been defined, it's just going to say, oh, I don't know what that is because that doesn't exist, right? And so the other thing to point out, right, is that R is case sensitive. And so if you're using capitals, they're not interchangeable with lowercase. Common error, especially when we're like using functions, and you might capitalize something accidentally. Okay. So I just described the way that you store data as an object as using this caret. But actually, I can do this, and this operation does work, and it will operate in the way that you think most of the time. There are some corner cases where this actually will produce aberrant behavior. And so in general, it is recommended to use the arrow instead of the equals. Yeah. Do you have a question? No? Okay. Yeah, and so if you're used to Python, I would still recommend you kind of use this procedure. It'll get you out of trouble in some cases when we're doing like certain types of inputs for like functions and those sorts of things. Any questions? No. Okay. I can store multiple objects, obviously, and so I've now defined object y as storing the value 3. And as I showed before, I can call in objects that have already been stored. So if I put in x, it returns 2. Put in y, it'll return 3. And if I put in x plus y, I'm adding these two objects together. What gets returned? Come on, guys. I know you can do it. Yes, 5. All right. Great. I can also overwrite objects that have already been defined. Okay, and so we previously defined x as 2. Here, I'm going to redefine x as 3. We view in the environment window, right, x value is now 3. And so if I do x plus y, this time I get 6. Yes, great. Perfect. Okay. We're going to talk in a little bit more detail about functions in a little bit, but I kind of need to introduce this guy first. And we'll get to a more generalized description and definition of functions in a little bit later. But concatenate is kind of one of the most commonly used functions in R, right? And so a function, right, is I have some kind of input, I put it into a function, and I get some kind of output, right? And so the function here is C, and then the things that we put into C are the input, and then whatever, when I hit enter, right, or command enter, and I pass it to the console, that's going to result in some kind of output. So I'm going to put in a couple of numbers separated by commas. Oh, and I should mention this is called the concatenate function, and it's represented by what is outside in front of the parentheses, so C. So if I hit enter, what you'll notice here is that the console returns essentially 1, 2, 3, 4. Okay. So I know that most of you who are familiar with R, you're looking at this. This is all kind of fine and dandy. But there are a couple of details to really kind of pay attention to in a second here, okay? Actually, to start off with, does anyone know what this number here represents?
That's the number 1 is the first of
So let's. I'm gonna try and be as precise as possible here. So calling this an object would not actually be accurate, right? Because this entire thing that got returned is actually the like one object, and then contained within it are specific numbers. But the point that you're making is correct. So that bracket is telling us uh, the position index of the first thing in that line. And so what I mean to say is if I do 1 to 100, you'll see that in the first line, so the first index of this object is 1. The 12th index location in that object is 12, and so on, right? And so you can easily tell, right, when you're looking in the console and it's got these square brackets, it tells you the position of that starting number. Okay? Okay, so let's think about, oh, and sorry, so I should say this thing that I returned here, this is known as a vector object. So that is an object that basically contains multiple numbers. All right? And we can think about doing operations with vectors. So x1. So I'm going to create a couple more objects. I'm going to create x1, x2, x3. Okay, and so I'm going to run these guys. And here you'll look in the environment and you see something a little bit different. You see numeric 1 to 2. That's actually describing the characteristic of the vector. So what is contained inside of the vector are numeric values. All right. Let's do x1 minus x2. We run that and we get 0, 0. Great. So what's happening, it's saying x1 minus x2, I'm going to take the first position and I'm going to subtract it from the first index position number in the second object. So that's 1 minus 1 is 0. And then in the second position, I'm going to do 2 minus 2, and that's also going to be equal to 0. All right, x3 minus x2. Okay, do not execute this yet. For all of you guys who are experts in R, without running this, tell me what gets returned. Any ideas? Since everyone here knows, right? Or maybe we'll learn something today. All right, who thinks that it's going to give an answer? Raise your hand. Who thinks it's going to be an error? Raise your hand. Well, so here's your first warning. And actually, I should be a little bit, okay, let me be more precise. So I asked if it was going to be an error. And what you see here is a warning. So there is a fundamental difference between errors and warnings in R, right? So an error means you perform an operation and it cannot do it. And so it will error out and it will not give you an answer. A warning in R is, okay, I will actually do what you asked. I'm going to give you an answer, and it's going to say, warning, you did something weird, and the answer that you're getting might not be what you actually expect. Okay, and so that's what it's doing here. So be careful of these things, right? You may be running, there are operations in R where you would think that if you did it incorrectly, it would break. But in this case, it actually is providing an answer. And that answer is going through a specific procedure. It just might not be necessarily the answer that you're looking for. So can anyone explain what you think this answer is representing, 002? Yeah.
First and second positions are subtracting from each other
Yep.
identically, but on the third position it's taking the 3 and recycling x2 so that it takes
Yeah.
-1.
Yeah, exactly. So we go 1 minus 1, 0, great. 2 minus 2, 0, great. 3 minus, there's nothing in the third position. Let me go back to the start of my x2 vector. So it's 3 minus 1, and that's 2. So my answer that I get is 002, and that's accompanied by this warning that's like, hey, you did something kind of dumb. So maybe be careful. Okay. Any questions? All right, so let's move on. I can also do, right, I mean, this is kind of the same thing, x2 minus x3. Instead, it's recycling on the first vector, and so 1, then 2, then back to 1, and so it'll be 1 minus 3 in the third position, so you get -2. I can do multiplication, right, and that should be as we intuit. Now, if I do x2 times x3, and we carry forward the logic of what we did for the subtraction, it'll be the same thing, right? So 1 times 1, 2 times 2, and then 3 times the recycled 1. So we should get 1, 4, 3, and a warning. And there it is. That exercise that I just did, I encourage you guys to actively try and do this type of thing when you code, is that when you're executing code, you should have in your mind some idea of what you expect the outcome should be. And that means that you know what you're doing, and if there's something contrary to what you expect, right, then you know that you might have to look into it, that there might be some kind of problem, right? Or that your understanding of what's going on it isn't perfect. And so that's good practice to be proficient at coding. That kind of extends to thinking about the use of like AI in code. We ask AI to help us with the code. And the kind of easy way of doing it is just like taking that code and running it, but really at the end of the day, we want to be understanding the code that we're executing. Okay, x1, we can also do division. This shouldn't be unexpected, but just know that's that operation that you can divide vectors, you can multiply, you can add and subtract vectors, no problem. I can also multiply vectors by constants, in which case that constant value will be multiplied across the entire vector. So x3 times x4 should yield 4, 8, 12, right? And so that's what we see. Great. So we won't really do this type of operation in this class, at least very much. But you can do matrix-based operations. And so if I wanted to do matrix multiplication of 2 different vectors, right, which is different from doing these products that I described before, you can do that. And the syntax for that, for those who aren't familiar, you do percent times percent. And that will let you do matrix multiplication operation. And so if I do x1 matrix multiplication times x2, you get this quantity 5, and they actually stick it into a matrix form for you. We'll talk about that a little bit more later. And then you can do things like transpose vectors if I want them to be, vertical or horizontal. So that'll turn that into a matrix as well. we're not going to do much like matrix manipulation in this way in this class. This is kind of just for reference for those who are interested. And so we can be a little bit more complete here. Okay. Any questions about any of these operations so far? All right, so we'll move on. We'll talk about functions. Okay. So functions can be these sort of enormously helpful tools for us. Many functions are built into the base capability of R. Some are coming out of packages that you can download and install and then use kind of freely. And the idea is I have some, again, right, a function is all about some kind of operator. I take an input, insert it into my function, and I get some kind of output. So right now, what I want to do is to introduce a bunch of base level functions that are in general going to be really useful for you guys. I suppose since a lot of you guys are familiar in R, most of these should be familiar, but maybe some of these will be new and helpful. Okay, so the first function I'm going to tell you guys about is the help function. This is the function that tells us about other functions. So if there's ever a function that we don't know how it operates, what are the inputs, what are the outputs, the help function is a great way of understanding that. So what was the first function I introduced to the class? Concatenate. So if I wanted to learn about concatenate, I can type help C and enter, and then in the bottom right corner where I described, the sort of visualization part of the UI, that's where it'll give us some information about this function. Combine, not concatenate, sorry. I need to fix my notes there. The combine function. So if I put help C, it'll tell me about how, this is a generic function which combines arguments, so it gives you a description of the function. It tells us how to use it, so C, and then you put in inputs, and so what are the arguments? And then, you can go through all of this stuff, and usually one of the helpful things is at the end, it'll give some examples of code that you can run using those functions, and it tells you a little bit about kind of what that does, right? So as I go through these functions, as I go through functions in general throughout the course, there's certainly going to be functions that you guys have not seen before. If you ever need to review or recall kind of official documentation on what a function does, you can use the help function. We can even do, actually I've never tried this before, but there. You can even see what the help function does. Very meta. Okay. LS. Who can tell me what LS does? Yeah. Yep. So LS, sorry. I'm thinking of RM. So actually LS is the list function that tells us all of the objects that are currently stored in our global environment. Okay, so we've defined a bunch of objects prior to this, right? I can look at the environment window to see what those objects are, but I can actually list them out here as well using the ls function. Okay. The ls function actually returns a vector of the object names. We're gonna look at this in more detail, but there's something a little bit different about this vector. Can anyone tell me what that is? Yeah.
It has a quotation mark.
Yeah, there's quotation marks around each of the objects, right? So keep that in mind. We'll get back to that in a bit. Okay, RM. I think this is the function that you were thinking about. So this is the remove function, and this can remove an object from the global environment. So if I do rm of x, that means please remove this previously defined object x from my environment. I hit enter. You'll see up in the global environment, there is no longer a listing for x if I type ls, which is our function we just looked at to list the objects that are stored. You'll see that x is now gone. Okay? How do I remove all of the objects that are stored in my environment? Using the power of two functions. What do you guys think? Any ideas? Yes.
Would you do RM and then inside RM LS?
Yeah, RMLS, like so. And so it says, give me, RM is tell me what objects remove, and you put in the ls, which gives it a vector of the object names, and it will remove all of them, or will it? So why did that happen? Any ideas? So if I type in help rm, yes. The problem is that I can only actually feed it the specific object to be removed or the name of the object, but you've actually fed it a vector. And so if I wanted to do, if I wanted to remove all of them, then I would have to use a particular argument specifying that I'm giving it a list or vector as opposed to one object. So I believe we can do it this way. List equals ls. There. Okay, and so up here in the help function, it's telling us that there are other arguments that we can make in our inputs, and list being one of those arguments, and I set that equal to the vector of the object names that I want to remove. So you can do rm list equals ls. Okay? So this would be the same as, okay, so if I just to be abundantly clear about why that didn't work, essentially what we did was something like well, I guess it's not quite what we did, but yeah. So if I tried to remove multiple objects in this way, I guess this actually does work because they've designed this particular function to be flexible to take in multiple objects named like this way, but not as an individual vector object without specifying it as so using the list. Okay? So that's RM. Any questions? Okay, a couple other ones I hope should be pretty obvious. So mean. So what happens if, let me put in my x1, x2, and x3. and my x and y back in. All right. So what do you guys think mean means? The mean. Yeah, the average, right? Okay, and so what happens if I do mean of 2, 3, 4? What do you guys think? Yeah. What's the average of 2 plus 3 plus 4? Come on. It should be 3, right? 2 plus 3 plus 4 is 9 divided by 3 is 3. We're going to have real problems in this class, guys, if you can't do this. Okay, so I hit enter, and it told me the answer was 2, right? So what the heck just happened? Did we just break math, guys? All right, so let me help you guys out here. What about if I did this? Okay. So what does that mean? What does that mean about the input requirements for this particular function? It is expecting a vector of our numbers, right? And so it's actually just looking at the input in the first position of our arguments, and it's doing the mean. And so if the input argument is just what is the mean of 2, it's 2, right? And so that's why there's a big difference between doing this versus this, okay? So in general, right, as you guys are doing R and running this code and you run into aberrant behavior like this, oftentimes that has to do with the way that you're inputting things into functions, so that's something to be careful here. I was actually surprised. I thought that there would be even a warning, right? But here you're getting the wrong answer and no warning, so you need to be doubly careful sometimes. Sometimes you won't even get a warning. All right? Okay, any questions about this? Nope. All right, we'll keep going. Length is a handy tool to tell us the length or how many numbers are contained in the actual vector object. And so if I do length of x3, for example, we expect that to be 3, right? Because there's 3 numbers. Great. End row and end call, number of rows, number of columns. We'll get back to this once we actually deal with 2D objects. Max. And here we'll do a similar type of thing. Max 234, max T34. And in this case, this particular function is designed with the flexibility in mind that you can put in multiple arguments to consider as opposed to just one object. But in this particular case, you can do both. Sample is a very handy function, particularly if we're doing things like bootstrapping. So sample is just randomly sampling from something, okay? All right, so what are the arguments that I put forth here? So X, these are the things that you're sampling. So imagine if I have my hat, I put a bunch of numbers into the hat. Those numbers that I put into my hat, those are my X. N are the draws. So how many times I reach into my hat and pull out a number, that's N. And then the last one is replace. which is an argument that tells me if I sample out of my hat, do I put that number back in when I do the next draw, or do I keep it out? Okay. All right, so if I want to, for example, sample from a vector of 1 to 100, and I want to do that 50 times, then I hit enter. Great. I have a hat that has numbers from 1 to 100, and I reach in and I'm picking them out one at a time, and I get 50. I draw 50 times, and that returns a vector of these 50 numbers. Okay, that vector goes from 1 to 50. What is the number? What number is in the 16th position of this vector? 35. Cool. How did you count to 16 really fast?
Number 3 is in the 12th position.
Yeah, exactly, right? So this is a very fast way of understanding where in that index we are. So if I wanted to say, oh, what is the 37th index number of this vector, it would be 34, 74, 66, 85, and 25 would be our measure number. Cool. You'll notice here that I did not enter in an argument for replace. What do you guys think? Looking at this vector, do you think that this was sampling with or without replacement? Raise your hand if you think it was sampling with replacement. Raise your hand if you think it was sampling without replacement. Yeah, okay, good job. We know that it's sampling without, well, we don't actually know by looking at this. It would be statistically improbable for it to have been sampling with replacement, because we have no numbers that are repeated. It would be very, very unlikely. You know, it's the same thing as the same birthday trick. You guys know about that? We have 34 people in here, so there's almost certainly 2 people in here with the same birthday. Yeah, we can figure that out later. All right. Yeah, so if I actually say help sample, you'll notice in the usage part, it's got this thing replace equals false. So I can set replace equal to true or false, depending if I want to sample with replacement or if I want to not sample with replacement. And what it's telling us here is the default is set to false. So if you don't specify something, it's going to be sampling without replacements. And if I do sample 1 to 100, 50, replace equals true, I will bet like $5 that we will have the same number somewhere. Yeah, 26 appears twice in position 22 and, 21 and 32. Okay. And if I sample 1 to 100, 101 times, what's going to happen? Is it going to work? Is it going to break? Is it going to give us a warning? What do you guys think without executing? You think warning? Okay. I think it's going to break because I don't think you can reach into a hat 101 times that only has 100 numbers without replacing. So error. It can't do it. Okay. Logically it doesn't really make sense. You wouldn't be able to draw 101 numbers out of a hat that only has 100 numbers. Okay. So there's our first example of a function actually breaking because it can't execute. Rep x and n. So this is saying repeat. This is a quick way to be able to repeat something a bunch of times. So I can do repeat. I'll type it up here. Okay, I want to repeat the number 2 10 times. Great. Hit enter, it returns a vector that has 10 numbers in it, all of which are the number 2. You can also do this for vectors. So if I want to repeat x1 10 times, I can do this. And so my vector x1 will get repeated 1, 2, 1, 2, 1, 2, 1, 2, and so on 10 times, right? I can even repeat each element of the vector 10 times. What's the difference between these two? Can anyone venture to guess here? Instead of 1, 2, 1, 2, yeah?
You just repeat the 1 10 times first and then 2.
Perfect. So 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 2, and so on. Yeah. And I guess you can do both. Each equals 10. What's the other argument? Is it by? Does anyone remember? By equals 10? I don't think it's by. Oh, hang on. Luckily, we know how to look it up. It is times. Yeah. 10 times each 10. Cool. So I have each element is repeated 10 times, and then each vector is repeated 10 times. Sequence. So earlier you guys actually saw me do this thing where I did 1 colon like 20, right? That generates a vector from 1 to 20. I can do that really rapidly. And that's a shortcut for sequence. So I can do the same thing in sequence where I can go 1, comma 20. And that does the same thing. Why do we use sequence? Well, actually, sequence is a little bit more powerful. You can go backwards, and you can also jump by specific intervals. So if I want to do 1 to 20 in increments of 2, I could do that. Oops. Right, and so 1, 3, 5, 7, or if I want to do 1 to 20 in increments of 0.5, I can do that as well. So 1, 1.5, 2, 2.5, all the way from 1 to 20. And as I was mentioning, you can go backwards too. Okay. Another function is called unique. So this is a function you put in vector input, and it will return all the unique values. So for example, if I wanted to do unique of, let's say, x1, right, that's just going to return 1 and 2 because the elements of that vector are already unique. But if I wanted to do unique of, let's say, a vector that's 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 3, 3, 3, then this will return 1, 2, 3. Any element that is repeated multiple times in the vector, those will get emitted. The last ones I'll leave us with are summary and structure. These are going to be really handy functions to look at some basic elements of specific types of objects. And we'll revisit this in more detail in a little bit. Okay, so this is at a very high level an introduction to a couple basic functions that I think generally you guys will use quite a lot if you're not already familiar with them. Hopefully we're talking about this in a way that makes the sort of understanding of these functions a little bit more robust. But the sort of other general thing that we need to think about here is that what about if I wanted to make my own function, right? And so you can do that. You can build custom functions in R. So let's take a quick look at an example of this. So let's build some custom functions. All right, so let's say, you know, we saw this mean function, and I just don't like that function. I'm gonna build my own function. It's gonna be called I'm the real mean, and we're gonna do something like this. So this syntax that I just put forth here, this is the way that we generically create any sort of function. And the way this works is we're assigning, right, we're creating an object in much the same way that we had before. So that object is called I'm the real mean. And the assignment operator is telling us, okay, we're actually going to create this function object. And so I specify function and then input. Okay. And it really is the same way that you would think about a function, right? So we have that input. We're going to write the details of our function inside of these squiggly brackets. And then we're going to define an output that this function returns. Okay, so if I have a vector of numbers, how do I calculate an average? I know this was hard the first time, but I think you guys got it now. So help me out here. I have a vector of numbers. How do I calculate an average? Don't be shy. Yes.
Sum of all numbers divided by the number.
Cool, yeah. So what I'm gonna do, I'm gonna break that apart a little bit. So I'm gonna start with the first thing you said, which is I'm gonna sum all the numbers. I guess I didn't actually talk about this function, but hopefully you guys can deduce what this means. So the sum function will take a vector and add up all of the elements of that vector. Okay? Then we divide it by, so what would I actually put here? We divide it by the number of elements in a vector, right? But I want to make this function generically able to handle vectors of different lengths. So I can't put in like a number here. So what do I put in? How do we calculate that? Yeah. Length, perfect. So we say the length of our vector will tell us how many elements there are in it. And then exactly as we said, our final output, which I'm going to call z, is going to be defined as x divided by y, which is the sum of all of those elements divided by the total number of elements in there. Okay, and I'm going to return z. So when I put return inside of my function, that's going to say stop what you're doing and give this thing as the output, right? I could put in whatever the heck I wanted outside of, well, you know, it'll break, but if I put in more operations after return, it's not going to see that. It's going to stop at the return, and it's going to spit out the output, and it's going to end, right? And so return is usually kind of at the end of your function. Okay, so let's go ahead and run this. So yeah, just from an operational standpoint, the way we would do this is you would select the entire function to run and hit run, and that will execute properly, or you would you would execute your run command on the first line of the function, and that'll run the entire function. I think it doesn't work if you run yeah, that's right. I still got it. Yeah, oh, I guess you could do the last line as well. But you can't run from the cursor inside of the function. You want to select the whole thing, or you want to be starting at the first line or the last line of the function. Okay. I'm sure most of you guys know this. All right. So let's do something like I'm the real mean. And let's do x3. So that was our vector of 1, 2, 3. What do we expect the answer to be? 2. And we get 2. Yay, all right, it worked. What about if I did that manually? 1, 2, 3. Doesn't work, right? Same reason as before. The way that we created this function is that it takes in one input. If I wanted to do something like this, I would have to specify some generic, set of, well, yeah, you couldn't actually make it dynamic in a straightforward way. Well, you can, but we're not gonna talk about that. Okay, so make sure that your input matches when you're actually running the function and what input that you're putting in. Here's another thing to note. Yeah, so this may be a little bit newer or less familiar, even for those who are familiar in R. So let's take a look at what we just did. I'm the real mean. I put in x3, so x3 is my input. What is the sum of x3? It's 1, 2, 3, right? So that should be 6, so x is equal to 6. So I've defined within my function x as 6. And yet, despite having run through the function and executed it, and here I should have seen something where x gets redefined into the sum of input. So I would expect over here that x is equal to 6, right? But we can see that's not the case. So can anyone explain why that's happening? Yeah.
I'm guessing we didn't run that specific line 72 on its own at all.
Yeah, but I mean, we've run the function, which means that essentially at some point it had to execute this thing, right? And yet x doesn't get redefined even though it moves through that function. Yeah.
The x inside the function is only defined locally and it is not defined globally. So.
Yes. Okay, this is a very important concept in computer science. We are operating in different environments, okay? So everything in a function stays inside of the function. That operates outside of what we call the global environment where we're storing our objects. And so if you are defining things inside of the function, they will not change objects defined outside of the function. There are many reasons for this. We don't necessarily get into this from a practice perspective. And then, there's like maintaining kind of your namespace without polluting with too many objects and naming variables. But anyways, suffice to say that anything that's happening within here stays in here without affecting things in the global environment. The only thing that is communicating outside is what gets returned in our output. Okay. Any questions about that? Okay, so all of that having been said, this is unless there is actually a way to pass objects and store them from inside the function into the the global environment. Never ever do this. This is bad practice. I don't know why every year I tell people how to do this. But in case you really, really want to, if you really want to be a bad programmer, you can do this. Don't do this. You can run into big trouble sometimes if you do stuff like this. So if for some reason you really want to be a bad boy and you want to pass that information out into the global environment, you can do a double caret, and we can redefine our function, and I can rerun this, and look at that. Our x is now redefined as 6. Cool, now you guys know how to do that, and we'll never talk about it again and never do it. Bad practice. Okay, any questions? All right. Okay. Let's do loops and apply. So a loop is a particular procedure that's very handy when we do programming in general. Okay, so basically when you do a loop command, you are doing something over and over again. And the syntax we typically use for something like this is so the for loop, we have the inputs of the for loop, and then the operations of the for loop inside of the squiggly brackets. Okay. For x in 1 to 10, I'm going to do print x. So print just means return whatever the value of the object is. And so I run this, and it's going to print 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, and so you can put all sorts of things in here, and in the loop, it's just going to execute the loop over and over. And if you wanted to change values of the loop, you're doing that in the definition up here. So as I go from value, okay, actually the best way that I can kind of describe what's happening in a loop is we draw this on in a table. So if I say something like for x in 1 to 10, let me use a better marker, hopefully. Okay. Okay, we got a couple of tries here. Oh, even worse. Great. Oh my God, you are a lifesaver. Let's go get this back from me. So if I say for x in 1 to 10, something like this, the way that I kind of like to visualize this is with a table. So as I move through the loop, my value of x changes, and I say it'll go from 1, 2, 3, 4, and onwards. Now inside of the for loop, I'm doing some kind of operation, right? So this particular operation here, I'm saying print x. And so here, if I say print x, then in the first loop, it'll be 1, 2, 3. Okay, and so that's kind of obvious. But I could do other operations, right? I could do something like, what about if I did x times 5 over here, right? Then in the table, essentially the way I would think about this is x times 5, and each time I loop through, what would this operation result in? This would be 5, and then this would be 10, and 15, and 20, and so on and so forth, right? Okay, so that is essentially the way that loops work. yeah, so if I did x times 5, or I'm going to have to say print x times 5, you know, it'll loop through. So print 1, right? Each time it loops, it's going to give two things, the 1 and the 5, the 2 and the 10, the 3 and the 15, and so on. Okay. Any questions about this? We're straightforward so far? So even with these kind of simple set of tools, we can already start to think about more complex things that we can do. So I'm going to show you guys a sort of classic example of a function. This is very classic in like computer science. So if anyone has taken those types of courses, you might recognize this. So I'm going to ask you guys a question. So let me copy this and paste in here. All right. What does this function do? Okay. So function x. So my input is x. And let's just walk through this function together. So if my x is less than 2, so whatever my input is, if I put in a number that's smaller than 2, this function is just going to automatically return false, right? Hang on a second. Did we not talk about if else? All right, that's all right. Yeah, I'm realizing I don't have in here. Okay, sorry. I need to explain one more thing before we talk about this function. If function. Basically, this checks for conditions, and it's just going to return a true or false. Okay. And you can put in brackets, and basically, if true, if whatever thing is in if whatever thing that the if function is testing is true, then it's going to go into the square brackets and do the operation. So print the statement is true, right? And if it doesn't do that, then it'll skip what's ever in there. And if you want to catch all of the other things, you can have if else, and then else will catch anything that the if didn't. And so here we could print the statement is false, right? So if I run this, it'll say the statement is true. Okay, so if 1 is bigger than 0, will I enter into the first set of brackets or into the second set of brackets? The first one, right? Because 1 is larger than 0. The statement is true. But if I put 1 is greater than 2, is that true or false? False. So I will skip the first bracket and I will go to the second bracket. And so if I hit this, it'll say the statement is false. So that's how if-else statements work. So returning back to this particular function, okay, so remember what I was saying. If you're inside of a function and you ever hit the return part, it just ends, right? That's it. So if the input of this function is less than 2, then I'm going to just end and say it's false. Okay? Otherwise, it's going to continue on. So if I put any number bigger than 2, it's going to proceed over to line 96, which is my for loop. And it's going to run through this loop from what? So let's take an example here. Oh boy. All right, so let's say we put in x equals 4. Do we return false in that first if statement? No, right? This is x, so 4 is not less than 2, therefore it's false, then we just jump over to the for loop. So 4 in 2 through x minus 1. So what is x? X is 4. So we're going to say for n in 2 through 4 minus 1, aka 3, we're going to execute this stuff. Okay. Oh, I need to show us one more thing. Sorry. There's an operation here, %%. All right, for 10 imaginary points, who knows what this does? Yes.
The remainder of a division.
Yeah, great. So it's called the modulus operator, which is remainder. So what is 5 mod 2? It's 5 divided by 2, which is 2 remainder 1, so it's going to return the number 1, right? And so if I do 11 mod 7, 11 divided by 7 is 1 remainder 4, and so it'll return 4. Okay, so we're going to do n, and then we're going to look at 4, which is our x, mod of n. Because that's how we're moving through the for loop, right? So in the first one, so n is 2. 2, what's 4 mod 2? 0, right? There's no remainder. So does the remainder equal 0? It does. We're done. It ends the function because we enter into that if space because that statement is true, so return false. So if I were to say, what does this function do where x is equal to 4, this returns, oop, hang on. Could not find function because I didn't define it. Thank you. Okay. It returns false. Can anyone tell me what this function does? Not you. Yes. Yeah, great. So if you divide my input number by all numbers from 2 through that input number, and none of them give you a remainder of 0, which means it's not divisible, that means it's a prime number, right? So with just a couple of these tools, we can put together this nice little function that tells us whether a number is prime. So I can, yeah, so this function is called isPrime. Okay, and I'm gonna redefine this. I'm gonna call this isPrime. Is 4 a prime number? It is not. Is 5 a prime number? It is. Is 97 a prime number? It is, right? And so what this does is it takes whatever number you give it, and then it just continuously divides numbers until it finds something that it's divisible by, that it's not itself. And if it's divisible, then it's not a prime number. Got it? Okay. Is prime 1 second. Where's my cursor? Here we go. I think I need to find a bigger number because, like, as I've done this over the years, the computers have gotten decently fast. Okay, so here is 9,999,000 or 99,999,989 a prime number. Yes, it is. And actually, let me do something real quick. Don't worry about this code. I'll describe what it does. We're measuring the system time as a way to calculate how long it takes for this function to execute. You're essentially storing the system time, running the function, and then taking the new system time minus what you had stored. So this tells us essentially how long this function takes to execute. All right. So this function takes 7.73 seconds to execute. This used to take 30 seconds when I had a slower computer first teaching this class. Okay, but I don't want to wait like 10 seconds every time I want to calculate a big prime number, right? This function right here, is this the best way to calculate a prime number? Can anyone think of a better way to do this? Yeah. Yes.
The last digit?
Huh?
Work with the last digit only?
Work with the last digit only.
Because if you're looking for a prime number, it's based on the last digit of the number.
Not always, right? Because like, if the last digit's a 7.
Oh, so a prime number. Sorry.
Yeah, prime number, yeah. So that might help in some ways. Anyone else? Anyone have any ideas about how? Do I need to do all of these numbers? Yeah.
No, like you don't need to check like the number right before, and you only need to check out to the square root of the number.
Yes, exactly. Right. So if you think about like the number like 24 or something, there's many divisible. Like you can go, or if I do 1 times a big number, 2 times another number. Okay, I'm explaining this really badly. Okay, big number, and then my starting point of a 2. You're doing 2. You may multiply many times, right, to get to a number, but actually you've already counted this one somewhere earlier on, so you only need to get up to the square root. So yes, that's exactly right. And so we can make a better function by doing something like this. Okay. So the only difference here is that you'll notice in line 108, instead of going for n from 2 through n minus 1, I'm now doing 2 through the square root of my number. The floor is to round down. That's another function. So there's the function to round down is called floor, which makes the function to round up called, it's the opposite of the floor. The ceiling, yeah. So those two more functions to know about. So I just take the floor of the square root, and that's going to calculate is prime in the same way. Okay, and in fact, we can see that explicitly here I'm going to copy and paste this guy. Oops. Wait, hang on, sorry. So the first example took about 8 seconds. This example took 0.00262 seconds. Okay, and so you might think, well, 8 seconds isn't like that long of a time in the grand scheme of things, which is true. But this is running, what, on the order of like 1,000 times faster, several thousand times faster. And this is we're not in a computer science class, right? So why am I talking about these like functions? I think it's more about this idea and concept that when we think about things that are computationally complex and that take time to run, especially when we're doing data analysis on like large data sets, there's times where when we're programming and we're writing code, you want to make the code kind of as like the number one priority is always to make the code kind of digestible and understandable as possible, so that not only you can recognize it when you go back to it later, but also others can read it. There are times when you start running into issues where code takes a really long time to run, and there you often need to think about strategies to really improve the runtime in sort of nonlinear ways. Okay, so this is a concept known as big O in computing, and so what I would say is, in general, if you're running into computational complexity issues, try and look for strategies and solutions that are sort of putting your runtime into like different classifications of how complex they are, right? The first example will scale linearly with the size of my input, right? Whereas the second one scales with a root n, the root of the size of your input, which is like magnitudes different, right? That's what's leading us to these sort of thousands of differences in runtime. So that's one thing to think about. I'm going to show a different, I'm going to show a different example that's related to this concept. Okay, let me get rid of this. Okay, so one of the common ways that you can actually do this type of reduction is in reference to for loops. Okay, and I think for loops is something that we use very commonly in programming. So I'm sure that all the folks here who raise your hand about being familiar with R, that you guys have all used for loops before. So R as a programming language, actually, their implementation of for loops is quite slow, and actually not a very efficient process. And the sort of plus side is that for loops are very digestible. They're easy to understand, right? So we walk through this, and hopefully most of you sort of understand how that works. And so generally speaking, if you're not running into computational issues, for loops are often a really nice way of dealing with certain issues. But as kind of one of the most common areas of like bottlenecks for computational speed, I just wanted to show kind of an example of that. So here, what we're doing is we are creating let's see. I'm creating, in this part, you don't need to copy the code for. I'll just mention all of the code is going to get posted online. And so sometimes when I copy and paste big chunks of code, that's often when I'm like not asking you to follow along. You're welcome to type this out if you want, but just know that this is going to be posted on Canvas after class. Okay, so I've created a data frame, which we haven't talked about yet, but it's basically a table. It's got 100,000 values for two variables, x1 and x2, which I just chose randomly from 0 to 1. And what I'm doing in line 129 through line 131 is I'm just saying, okay, you have two columns, x1 and x2. I want you to tell me the average value of every row of that table, okay? So I'm asking it to do it in a for loop, and in the for loop, every time it's gonna look at row 1, take the average, it's gonna go to row 2, take the average, it's gonna go to row 3, take the average, and so on. And it's gonna do this 100,000 times for each one of the 100,000 rows, okay? So let me run this and we'll see how long this takes. We can sit back and twiddle our thumbs. Okay, so it took about 4.5 seconds. Again, man, computers are getting really fast these days. That used to take like a minute. Okay, anyways. There is a class of functions that I personally think are really not so intuitive in R, but these are ways where I can kind of parallelize operations that you might do many times. So this is a fantastically fast way of doing things you might ordinarily do in a for loop. So I am kind of showing this particular example as kind of the most common example of where people run into computational complexity, where things take a long time to compute. If it's because of a for loop, I would look towards this class of functions called apply to replace it instead. So this apply function is doing the exact same process, the exact same thing, and let's see how fast it does it. Okay, so an order of magnitude faster, and that will scale quite a bit with the size. Yeah, so just one little sort of tidbit of advice that comes from some experience. If you're running inefficient for loops, this is one area to consider. Okay. Okay. Any questions about this so far? Okay. So let's see, we have data types. I think we can, let's end a little bit early today. I think this is a good place to kind of separate from tomorrow. So yeah, that's our first day tutorial of R. I think most of you are probably familiar with most of these concepts. Hopefully we're adding a little bit more rigor and understanding to some of these things. But we'll continue with some more fundamentals on R on Thursday. And then from there, we'll dive into kind of the data analysis portion. All right. Thanks, everyone. I will see you guys on Thursday.